Hello everyone, I am Ashutosh Makone. I work as a data scientist in London and I'm starting with this YouTube channel. The name of the YouTube channel is Code Hopper and my first tutorial is on PyTorch. So it will be a tutorial series and the first thing you encounter in PyTorch is tensors. So tensors is a special type of data structure that is quite similar to arrays and matrices, and they can run also on GPUs, and they are optimized for automatic differentiation. So this differentiation part comes into picture when you deal with backpropagation. So for this series I assume that you have some understanding of deep learning and NumPy as well. So first thing first, you have to import the libraries, then how to initialize tensors. So I have a list data, and then from that torch.tensor and give this data, it will create a tensor for us. So if you run this, it will create a tensor of dimension 2 by 2. If you check the data type of data, it is a list, and if you check the data type of x underscore data, it is tensor. Now another way to create a tensor is from NumPy array. So from the list, I create a NumPy array and I give this NumPy array as an argument to this function from NumPy. So torch dot from NumPy will create a tensor from NumPy array. So at the output we get a tensor of the same size and same values. Then another way is to create a tensor from another tensor. So the function is ones like. So it will create a tensor with all ones inside it, and its dimensions will be like x underscore data. So x underscore data is a list of lists whose dimensions are 2 by 2. So this tensor will have a dimension of 2 by 2 and will have all ones inside it. If you run it, you will see all ones dimension 2 by 2. Then rand underscore like is another function which creates a tensor of random values of the same dimension of x underscore data, and you can also specify the data type as float. So if you run here, it creates a tensor of size 2 by 2 with all random float values inside it. Then there are different functions. For example, torch.rand will create a tensor of this shape which is 2 by 3, and it will have all random values. Another one will create the tensor of all ones, and third one will create the tensor of all zeros. So if you run this, a tensor of size 2 by 3 with all random values, a tensor of size 2 by 3 with all ones, a tensor of size 2 by 3 with all zeros. Then you can get the attributes of a tensor. So tensor.shape gives the shape of the tensor, tensor.d type gives the data type and the device on which it is running. So first we create a tensor with random values and size 3 by 4. So if you run it, you get size is 3 by 4, data type is float 32, and right now I'm working on a CPU, not on a GPU. So that is why this is the output. So these are getting the attributes of a tensor. Then there are more than 100 operations that you can perform on tensor, including arithmetic operations, linear algebra operations, matrix manipulation, and all. And by default tensors are created on CPU. So if you want to make the operations on GPU, you have to explicitly move them to GPU using two methods if the GPU is available. So first, while performing these operations, you have to check if the GPU is available by or not by using this torch.CUDA is available. If the GPU is available, then the tensor will be moved to GPU, and then it will perform rest of the operations on GPU. So you can also perform standard operations that you can perform in NumPy, like indexing and slicing. For example, a tensor of ones with 4 by 4. So this is a tensor with all ones and the dimensions are 4 by 4. And if you give tensor of 0, let me run this. Tensor of 0 will give the first row. Let us print the tensor here. Print tensor. So this will give the this is the tensor that we have, all ones and dimension 4 by 4. Tensor 0 will give the first row. Tensor colon means all rows and 0 means 0 column. So it will give all rows and 0th column. So 0th column has got all ones, and you can check it with different numbers also. And this will also give the same. It will give the tensor with the last column. -1 means the last column. And if you make tensor colon 1 equal to 0, that means the first column and all rows, first column, this is 0th column and this is first column, so first column and all rows are made equal to 0. So this element, this element, this element, all these will be made equal to 0. So you see here the first column is made equal to 0. So this is how these operations are performed. Now how to concat tensors? So torch.cat is the function, torch.cat, and you give first the tensor, and I am giving the same tensor and giving the same tensor. Thus the same tensor is given 3 times. So the right now the tensor has got, looks like this, the tensor looks like this. So if you concatenate to itself 3 times, then this is the first tensor, this is the second tensor, and this is the same tensor third time. Yeah, and this dimension 1 means all the columns will be attached. Now if I make this equal to 0, then it should append row by row. Yeah, so it will append rows below rows like that. So this is how the dimension changes, right? So this is how the tensor looks like. All right. So the tensor that we have created here, we are going to use it for further operations also. So just for the sake of reference, this is how our tensor looks like right now. And now we are going to go into the multiplication of tensors. So there are 2 types of multiplication. So if you have learned in mathematics, if you have learned matrices in mathematics, you know that matrix multiplications are done either element by element matrix multiplication or proper matrix multiplication, where you multiply first row with first column and add the elements, and second row with second column and add the elements, and all that. So that is called as proper matrix multiplication. So 2 types, one is matrix multiplication and one is element by element multiplication. So if I run this, this performs proper matrix multiplication. So this is here, this @ symbol is used for multiplication, and it will multiply 2 tensors. The first tensor is the tensor itself, and the second tensor is the transpose of the same tensor. You can take another tensor also here to multiply. So here I am multiplying the tensor with its transpose. So if you take this tensor and if you take its transpose and if you multiply with proper matrix multiplication, you should get this thing. So it's like this row multiply by the first column of the second tensor and add the element, so that will become equal to 3 because there is a 0 here, right? Another way to multiply tensors is tensor.matmul. tensor dot transpose. So I am multiplying the tensor with its transpose. Again, y2 should have the same result. And third way is, first we create a tensor, third tensor y3. We create a tensor y3 with all random numbers and whose dimensions are same as tensor, and then this matmul function will take tensor as first argument and tensor its transpose as second argument. These two will be multiplied and the output will be assigned to y3. So if you multiply this, then y3 should look same as y1 and y2. So these are the three ways of performing tensor multiplication. Then if you want to perform element by element multiplication of the tensor, then you get this. So we get basically the same because we are multiplying 1 by 1 and we are multiplying 1 by 0. If you want, you can try something else here. So for example, if you take the transpose of it, then you get something else. So transpose looks different, isn't it? So just give me a second. Let me check how transpose looks like. Yeah, this is how the transpose looks like. So if you multiply, in our original tensor we have all ones, we have all zeros in the first column. In the first column means index 1 and position 2, there we have all zeros. So this, in the output you have got all zeros here. Here we have got all zeros. So in the multiplication also we have got all zeros, and everywhere else we have got ones. So this is how it is element by element multiplication. Then this MUL function again performs element wise multiplication. So tensor dot MUL, tensor will give matrix multiplication. Then again this is MUL. This is simply MUL. It performs element wise multiplication. Here it was matmul. Both have similar syntax but their names are different, so it is matmul and it is only mul. So it will perform element wise multiplication between these two tensors and the output will be returned to Z3. So this is element by element multiplication. Then this is sum of tensor, and then we want to get the atom. So we get the atom from the tensor and then we print both of them. So for example, yeah, so the atom is 12. So if you print AGG here, you should get a 12, because adding all the elements in this tensor gives 12. So that is why we are summing everything and this becomes 12. And this is now a tensor. We want to get the value in the tensor, the atom in the tensor. So it is dot atom, that gives the atom. So if you print the atom, it gives 12, and if you print its data type, you will get float. And if you print the data type of AGG, it will print tensor. Simple. Then there is a concept called as in-place operation. So generally when you perform operation between two variables, the result is stored in third variable. But sometimes, suppose you want to print the tensor here, first we print the tensor here and then we add 5 to it. So because of this underscore, the original tensor is going to get modified. So if I run it, we get this. So every element is added with 5 because it is 0, that's why it is 5 here. all the other elements have become 6. So if I remove this underscore, and now if I we have modified the tensor already, so it's not going to work like that. Okay, let me just get the original value of tensor. Okay, this is how we get the original tensor. And now if I execute this without underscore, it will not display the added values because the addition is done but the tensor is not overwritten. And when you give underscore here, then the original tensor is overwritten and you get the new tensor. So this underscore is always used when you want to overwrite the original tensor. This type of operations are called as in place operations, right? So they overwrite the original tensor. Then how the numpy array and tensors interact with each other? So you can create a tensor of all the ones with 5. So if you run this, you get 5 ones in the tensor, and then t.numpy will convert this tensor into a numpy array. So you get this as a numpy array. So initially we create a tensor, we use this t.numpy to convert this tensor into numpy array, and this is what we get as a. So if you just want to check, you can check the type of n, it's numpy, and if you check the type of t, it's tensor, right? Then this is again in place operation because we have given add underscore 1. So here we have created a tensor and we have created a numpy array from that tensor. Now one important thing to remember is, if you modify the tensor, because this add underscore will modify the original tensor, if you modify the tensor, it will also modify the numpy array. So a numpy array is created from tensor, we modify the tensor, the numpy array also automatically gets modified. This is because of pointers. There is a same pointer which points, the memory pointer which points to the tensor and to the numpy array. So when you modify the tensor, the numpy array automatically gets modified. So this is how it works. Yeah, right. And like opposite operation, first we create a numpy array, and then from that numpy array, if you want to create a tensor, then the function is from numpy. So torch.from numpy n will create a tensor from numpy array n. So if you want to check n, it looks like this. This is a numpy array. If you want to check t, it's a tensor with the same values. So first we create a numpy array and from that we create a tensor, right? Then again, if you change, for example, if you add np.add, we have a numpy array n, we add 1 to this numpy array and output is overwritten on n. That means numpy array is going to change in this case. So if you change the numpy array, the tensor also changes. So it's vice versa. If you create a tensor from a numpy array, and if you change the numpy array, it will change the tensor as well. If you create a numpy array from a tensor, and if you change the tensor, it will change the numpy array also. So that is how it works. And if you don't want this to happen, if you don't want change in one of them to affect the other, then there are other ways that we will learn in different tutorial. All right, so I hope the basics of tensors are clear to you. Slowly we will move into the depth of PyTorch. uh, Goodbye for now. Thank you.